Okay, I'm hoping for this one to be ridiculously short. I want to work on the triangle mid-segment theorem, really, and then we'll deal with some unique shapes. Nothing out of the ordinary, just things you might not have seen along with things you have seen. Okay, this one is from the book, and I changed my name and changed the problems a little bit. So as I'm drawing shapes on my paper, he drew a line segment that connected the midpoints of two sides of a triangle. So I'm looking here and here. I have an entire line, and it D is the midpoint of AC, so it divides it in half. AD and CD are congruent, and E is the midpoint of CB, so CE and EB are congruent. These are called mid-segments. I'm sorry, this line is called the mid-segment of the triangle. And this is just one mid-segment. I can do another one here and here. I'll do them later. Mr. Robinson says, I wonder what we can find out about this mid-segment, he said to his team. Let's call that class for now. Examine his drawing at the right. Okay. Let's assume that this one is actually drawn to scale. I don't say that often. It's really to the right, but let's say that this is drawn to scale. So I'm actually going to make a line here. I want to see what the relationship is between DE, that is huge, between DE and AB. Now I'm going to, judge it and eyeball it, but for your benefit, let's make these and let's put these right next to each other so you can see. DE appears to be half the length of AB. Okay, that's just from me being able to drag it. You can use a ruler or anything else. And this picture actually is drawn to scale. Now I ask you to never assume pictures to be drawn to scale, but if they said, if you were to make a guess, what would you say about it? Given some things, right? Given the appearance of it, what does it look like to you? I hate to say that to you now because I always ask you not to assume things drawn to scale. But how do their lengths seem to be related? DE appears to be half of AB. Okay, Mr. Robinson wants to prove that AB is twice DE. So if DE is half of AB, then AB is twice DE. However, he does not see any congruent triangles in the diagram. Now he sees congruent parts, or I do. Congruent parts, but not yet congruent triangles. I don't know if I see any congruent triangles even when I start to prove. How are triangles in this diagram related? How do you know? Use a two-column proof to state your conclusion. Okay, now we can go off here. I have CD is congruent to DA. Okay. I know they're congruent, but I do not know, that does not tell me how CD and CA are related though. If I want to look at the two triangles, I won't even have that much room for this. Okay, let's just say we know the left side is statements and the right side is reasons, so I'm just going to put it up here. Okay, let's go back. I know CD and CA and DA are congruent, but I want to know what the relationship is between the triangles. So this triangle and this triangle. So I want to know the relationship between CD and CA. Well, if CD is congruent to DA, then CD is half of CD plus DA. Because if CD equals DA in terms of length, then I do CD plus DA. I can take CD and replace it for DA. So CD plus CD equals 2CD. So DA equals, or CD plus DA equals 2CD. So this is twice the length of that. So that's something that I know. So I can say CD, which one's CD? The small one? CD over CA equals 2 over 1. I'll say because CD plus DA equals 2CD. Same thing with the other one. If these are congruent, then CE plus EB is twice CE. So CB, oh, I'm sorry, this is 1 over 2. So CE plus or over CB is 1 over 2. For the same reason that CE plus EB equals 2 CE. Okay? Okay, the third thing, because I have to prove these triangles similar. They won't be congruent, because I have the same side ratios there. I have this angle here, C, congruent to itself. Now I want you to remember this reason. It's the reflexive property. This angle is shared in both triangles. Okay? Vertical angles are not reflexive, they're vertical. Reflexive means the exact same angle. So this is angle C is congruent to itself by the reflexive property. Okay, because I have same side ratios here and the angle in between is congruent to itself, then I can say that triangle, I think it's DCE is congruent to triangle ACB. I'm sorry, not congruent, similar, triangle ACB by side angle side similarity theorem, or conjecture. Okay, I should have given you more room for the 2-column proof. Sorry that this is a mess so far. The common ratio between side lengths and similar triangles. So we do have that in triangle, we have triangle DCE similar to triangle ACB. Okay, so we had CD similar to CA in that it's 1 over 2. And then we have CE similar to CB in that it's 1 over 2. So if these triangles are similar, the third one also has 1 over 2, and that's DE over AB. Okay? DE is half of AB. So before we just assumed it, we just thought it. Okay, now we know. We know that DE is half of AB. Okay, now Mr. Robinson wants to prove that DE is parallel to AB. Use the similar triangles to find all pairs of equal angles you can in the diagram. Then use your knowledge of angle relationships to make a statement about parallel segments. So I want you to remember one thing about similar triangles, and that's that you can prove them similar by angle. We couldn't here. We could only use one angle. But if triangles are similar, if they can be proven similar by angle, then that means in similarity conjectures, they do have all the same angles anyway. So I want to correspond to them still. I can't correspond sides. I can in terms of similarity, but they're all similar in their own way anyway. But the angles actually are congruent. So corresponding angles of similar triangles are congruent. Let's see, corresponding angles of similar triangles are congruent. CASTC. So angle D is congruent to angle A, and angle E is congruent to angle B. Okay? So now take a look at this for 1 second. Okay? Look at those and see what you can think about when you have those things. We're trying to prove that DE is parallel to AB. So just take a look at that. Okay, you got it? Alright, let's go back. Because I don't have a triangle there. Actually, no, I do down here. I just wanted you to take a look at it. So let's redo that. Okay, if I have these angles congruent, these are called corresponding angles. They face the same way on the same side of the line. They correspond. If a pair of corresponding angles are congruent, then two lines that are cut by a transversal are parallel. And same thing here, the same corresponding angles, same parallel lines. So, I mean, I'm not proving it, I'm making a statement, but yeah, so my statement, if angle D is congruent to angle A, they are corresponding angles. I'll just say, and angle E is congruent to angle B for the same reason, then those lines DE and AB are parallel. Okay? I'm going to go and erase these guys again that I just did. Triangle midsegment theorem in general then says if I can draw midsegments, so I have one there, I'll do two more. So here's one. I'm going to assume the other two, like that one's like there, and then like there. Okay, close enough. Okay, if I draw midsegments between all these guys, then the midsegments, how do I put this? I should have drawn these differently. This midsegment, as we saw, divided these segments in two. Okay? And the midsegment is half of that guy, and it's also parallel to that guy. So these two are parallel. Now, if I rotated this, you could see it better, but this midsegment divides this in two, along with this, okay? And it is half of this, and it is parallel to it. Okay? Same thing over here. This divides this into two, and this into two. We'll call this F. And EF is half of CA, and it's parallel to CA. Okay? So the midsegment theorem, let me type it out here. Or sort of. I'll read it off something first. A midsegment, whoa, that's big. Of a triangle, segment between two sides of a triangle is half the length of and parallel to the third side of the triangle. Okay? So the midsegments are the lines that cut them in half, and they happen to be, or cut these in half, and they're half the third side, and they're also parallel to that third side. I realize that this lecture is kind of iffy. Said it would be short. It's kind of getting long, so I'll go quickly now. Second page, if you flip yours over. Unique types of triangles. Okay. I'll be pretty short with these. Let's go with the ones that you know for sure. Let's go with the right triangle. Features a right angle, angle, and has legs and hypotenuse. Okay, only right triangles has those terms as far as triangles go. Other ones are just called sides. Okay, an isosceles triangle has two congruent sides and angles. Now the angles are opposite those congruent sides, so it wouldn't be this angle and that angle. If these two sides are congruent, it'd be this one and this one. Okay, equilateral triangle has congruent sides and 60-degree angles. They all have to be 60 degrees if they're congruent, because they have to add up to 180. Okay, an obtuse triangle has one angle greater than 90 degrees. An acute triangle has all angles less than 90 degrees. And a scalene triangle is just a triangle where no sides, ES, or angles congruent. So just a general one, it could be 4, 5, 6, and then 50, 60, 70, something like that. Okay, those are the different triangles you'll be faced with. I can't think of any other ones off the top of my head. Okay, types of quadrilaterals, I have 9. We've kind of looked at all of them before, except for 1, 2, I haven't really talked about, but they are what they are. Let's go and start with the rectangle. This time I'm actually going to kind of draw them out better. Okay, rectangle. Now these are all quadrilaterals, so they're all four-sided shapes, so I'm going to leave that out. 90-degree angles. Okay, that's what's specific about it. Sorry about that. A square has congruent sides, so it's a rectangle with congruent sides. It's a specific type of rectangle. Now I'm just stating the minimum thing that these things need to be these. Okay. A parallelogram, that is an up arrow. A parallelogram features opposite sides parallel. Okay. Now, like I said, there are a lot more properties in these guys. Just these are the distinguishable things about them. A rhombus is a specific type of parallelogram. That's not quite congruent. It's a parallelogram with all sides congruent. Okay. So these markings are important as far as unique identifiers. Okay, a kite. Now, we've said one thing about kites before, but I want to be a little more... the area of the kite's defined by its diagonals, so I do want to refer to the diagonals more so the sides. You can talk about the sides, but again, I don't know how to write something about them. I can say set of sides congruent, but two sets of sides congruent, but more importantly is the thing about the diagonals, and that is diagonals are perpendicular I wish my handwriting on this was better. And one diagonal bisects the other. Only one specifically. Okay. I'm only using a right kite because I don't know if we're going to come across it. But a right kite is just a kite where one of them actually meets at a right angle, or one set of sides as well. It would only specifically be one of them. So kite with one right angle. Okay? So that's this angle here. Just showing you specifically how it would look. Okay, a trapezoid. Let's do it. Now this will also be an isosceles trapezoid, but that's not the point, so I'll just make one here though. Trapezoid one set of parallel opposite sides. Okay, isosceles trapezoid is a trapezoid with non-parallel, or with congruent non-parallel sides. Okay, so those two. And finally a right trapezoid, which I'll just kind of draw. That didn't really work out. Is a trapezoid with consecutive. We've said adjacent in the past. I said it for a reason when I was talking about it before, but I'll say consecutive when I'm referring to these. Adjacent is when they're on like that side of each other. With consecutive congruent angles. I'm sorry, consecutive right angles, 90 degree. Okay. So those are my things that I want to write that are minimally spoken about these. These are unique identifiers about these. There are more features to them, obviously, but if you wanted to say one specific thing and you wanted to identify it, there you go. Okay, this last bell is about to ring. That's it, and that's all. You have homework this can help you with it.